Hey everyone, welcome back. This is Junrao from Confluent. In this module, we're going to talk about how to configure some of the durability, availability, and ordering guarantees within Kafka. In some of the previous modules, we have to talk about how the control plane and the data plane works within a Kafka cluster. In this module, we're going to switch gear a little bit to talk about some of the guarantees. Let's first talk about some of the durability and availability guarantees. Earlier, we have talked about Kafka replication is a great way of providing durability and availability. So when you create a topic, you can specify the number of replicas you want to have. If you specified n number of replicas, then we can tolerate n-1 failures. For mission-critical applications, they can potentially configure even more replicas to tolerate more number of failures. Only the committed data will be exposed to the consumers. Now, what about the producers? The producers actually have some choices when to receive the acknowledgement. The simplest form for producer is to have this ACK equals 0 mode. This is a little bit like fire and forget mode. So it's pretty good for latency because you don't need to wait for the response to be sent. But there's no strong guarantee of durability because the data can be lost before even it reaches the broker. The second mode the producer can have is ACK equals 1. In this mode, the producer will wait for the data to be received and added into the log of the leader replica before the response is sent to the producer. In this case, the latency is longer because you have to wait for this round trip between the producer client and the leader broker. The durability story is much more improved, but there's still a little chance when there's like a leader election happens while a message is being produced, some of the records or events could be lost. The strongest mode we have is called XOR. If you configure this, then the producer will only be acknowledged once the data is fully replicated to all the insync replicas. This is actually the strongest mode for durability guarantees. And it's important for mission-critical application. In terms of latency, this is a little bit longer than the ACK equals more. It's roughly 2 times longer than the ACK equals more mode. Because in addition to the round trip between the producer and the leader, you have to wait for another round trip for the data to be replicated from the leader to the follower, potentially in parallel if you have multiple followers. But you have to wait another half round trip for the follower to acknowledge the receipt of those events. So it's roughly 2.5 times than the latency of the leader. Now, let's talk about some of the other guarantees. For some of the mission application, they may want to say, if I produce some records, I only want to have the records acknowledged successfully if it's guaranteed that records will be inserted into at least certain number of replicas. Otherwise, I'd rather I'd rather choose the data not to be taken. So this can be supported with a top-level configuration called minimum insync replicas. If you configure this, then when you append the data to the leads log, we will only successfully replicate the data and acknowledge it if at that point there's enough replicas, more than this minimum insync replicas, in the insync replica set. If there are fewer replicas than this configuration in ISR, then we'll send a not enough replica error back to the producer, indicating that your data is rejected. So this is another way for mission-critical applications to strengthen some of their durability guarantees. Now, let's switch gear a little bit to talk about some of the ordering guarantees. In the earlier modules, we have talked about, in general, we are already enforcing strong ordering from the producer all the way to the consumers. For the producers, for all the messages sent from a single producer to a given partition, they will be stored in the commit log for that partition in the order they are sent, and they will be delivered in the same order to the consumer in the normal mode. But sometimes the ordering guarantee can be a little tricky if there are failures. Let's consider this example. For example, in this case, the producer is trying to send 3 records, M1, M2, M3, into the leader. Let's say halfway through it, maybe only 2 of the records have been fully replicated and considered committed. But at that point, the leader is dead. and the producer didn't get any acknowledgement for all those 3 messages. Then, in order not to lose those events, what the producer needs to do is to retry sending those 3 messages to the new leader. So it will send M2, M1, M2, M3 again. In this case, since the new leader doesn't know this is actually a duplicate of the previous send, it will just forcefully taking those records in its log. Now you can see we have introduced some duplicates because M1, M2 have been received twice, and we are also introducing some of the violation of the ordering guarantees because now M1 appears to happen after M2, even though technically it's sent before M2. So to solve this problem, we have introduced another feature called idempotent producer. This is actually pretty easy to enable. You just need to set this configuration in the producer, enable idempotency to true. Once you have set this mode, I think the producer will try to avoid those duplicates and reordering even when there are failures. So let's see how it works. The way this works is when the producer is first started in this mode, the first thing it will do is to ask the broker for a producer ID. This is a unique ID intended for the lifetime of this producer. Then every time when the producer tries to send some of the events to the leader, it will tag all those events with the producer ID as well as the corresponding sequence number associated with each record. Those sequence number will be uniquely used to identify each of the messages the producer will be sending. Once the leader received those records, it will be appending those records with the PID and the corresponding sequence number in this commit log. And this will be replicated to other replicas as well. Now, let's say the same thing happened. Along halfway, you only have 2 messages, M1, M2, that has been fully replicated, and then the old leader died. In this case, a new leader will be elected, and when the producer was trying to resend the same 3 events to the new leader, it will be sending those 3 events with the same PID and sequence number. And once the new leader received it, it can compare those sequence number with the last sequence number it has seen with this producer ID. In this case, we'll notice that message 1 and message 2, based on the sequence number, those are duplicates because they have seen it before in its own log. So it will only take the last message, which is M3 in its log. As you can see, with idempotency introduced, now we can truly avoid the duplication as well as avoiding changing the ordering of those events. So this leads us to these ordering guarantees. If you have idempotency enabled in the producer and you also have ACK equals more or set in the producer, in general, we are guaranteed this end-to-end ordering guarantee. In particular, if you have a single producer sending keyed messages, we guarantee all the events sent with the same key, they will be landing in the same partition in exactly the same order they are sent, and they will be delivered to the same consumer in exactly the order they are sent. So this is actually end-to-end per key ordering guarantee we support. That's it for this module. Thanks for listening.